Hey guys, I'm Rakesh Aarya, your chemistry mentor. Welcome to Lecture 3 of Thermodynamics by Teach Tigers. Hope you guys enjoyed Lecture 1 and Lecture 2 and hope you guys got to learn some new things, some new concepts that are not very easily found in textbooks and classrooms. And following the same tradition, today in Lecture 3 also we're going to try and share some new things with you and clear some doubts that you might have had in your mind. So let's go. With the recap first, what did we do in the last two lectures? System is what we are trying to study. We defined our system. System is what we are trying to study. We defined what a system is in our last lecture, and we said there are three types of system. There's open system, closed system, and isolated system. Open system can exchange mass, can exchange energy. Closed system can exchange energy, but cannot exchange mass. Isolated does not exchange mass, does not exchange energy. It's kind of that guy that sits in the corner, does not share his thoughts, does not share his food. So isolated systems are somewhat like that. No exchange in mass, no exchange in energy. And we also talked about system and surroundings sharing a boundary. System and surroundings sharing a boundary. And what did we call it? We called it the system boundary. And we also said system boundary is of four types: adiabatic, diathermal, rigid, movable. Do you remember the meaning of all of them? Let's go one by one. Adiabatic. Heat exchange not possible. Diathermal. Heat exchange is possible. Rigid walls. Rigid walls do not do any work. No expansion, no contraction, no work done. Rigid walls, they just sit there, don't do any work. Movable walls, they can perform work, they can expand, they can contract. State variables have a deal. If this is my state variable 1, if this is my state variable 2, they have a nice deal with each other that wherever you go, I go there, or if you go up, I'll go down, let's play together. So state variables are kind of playing together. They're having a match of cricket, they're playing football, they're changing according to each other. They're sensitive to each other, they're like best friends. And the relationship that state variables have, the deal that they have, is called the equation of state. The deal that state variables make is called the equation of state. If pressure says, when I increase temperature, you decrease, that is part of the equation of state. If temperature says, when I increase volume, you should increase as square, that is also part of the equation of state. We also talked about internal energy. And what is the definition of internal energy? Internal energy is pretty much the sum of all kinds of energies you can think of. In mechanical terms, this is the sum of kinetic energy and potential energy. Kinetic energy comes from motion. Potential energy comes from height in case of gravitation, comes from interaction between particles, comes from interaction with an electric field. So kinetic energy comes from motion, potential energy comes from some other forms of interaction. We also defined that delta U of isolated system is 0. This symbol might not be familiar to you. What is this delta U that I'm speaking? Delta U. We took an example, an application in the last class where we said that the energy of an isolated system does not change. Why does it not change? It can't exchange mass, it can't exchange energy, so energy is not going to change, right? Nothing is going to happen to that guy sitting in the corner who's not sharing his thoughts, who's not sharing his lunch. He's going to be there sitting in the corner unless you break the isolation somehow, right? So we're going to talk about this symbol delta, which is written over here, and we'll talk about it in the coming slides. Today's concepts. What do we have today for you? We're going to talk about internal energy, more about internal energy. We already know the definition of internal energy, which is sum of all kinetic and potential energy. Then we are going to talk about first law of thermodynamics. If you understand this, you can answer more than 50% of the questions. If you understand first law of thermodynamics, you can answer more than 50% of the questions. And you can also talk about thermodynamics with confidence. If thermodynamics begins somewhere, it begins at understanding first law of thermodynamics. The very, very intricate details, very confusing aspects, which can seem daunting if you try to memorize them. Instead, what we are going to do, we are going to try and understand them. We are going to try and dig it up to find what's beneath the surface. And we're going to use that to just put it in the memory. Right? So, like for example, if you just like take something, try to stick it on the wall, it'll just fall down. Right? You first create a nice base. Right? A nice base, put some Fevicol over there, and then create a nice sachet, then put it over there. It's not going to fall. So we have to make it stick to your memory. We first have to create a nice base. You can't just throw things and expect some things to stick, some things to not. All right. Then we're going to talk about what is heat. We're going to talk about what is work. Internal energy, the first concept for us. We already know internal energy is the sum of kinetic energy plus sum of potential energy. So can U be defined? We already defined it. It's the sum of all kinetic energy and all potential energy. But if you go in details, it's very difficult to find the absolute energy of many systems. Very difficult to find the absolute energy of many systems. If I start talking about a very simple thing, just a few gas molecules. Now, gas molecules, they have kinetic energy. They might have some potential energy. Then, within the molecules, they also have potential energy. Nuclear energy is present within the molecules. Should we count that? Should we not count that? Does it matter? Does it not? So sometimes we don't really go about defining U very particularly, counting nuclear energy or radiations and all those things. Instead, we just say that it like does not matter as much as changes in internal energy. So our main focus throughout thermodynamics will be on changes in internal energy instead of internal energy itself. And what does this delta U mean? It means change in internal energy. It means U final minus U initial. It means U final minus U initial. We're going to take a very small example. I have here a measuring flask. In this measuring flask, I have measurements 10, 20, 30, 40. Some units can be milliliters, can be liters. I take a snapshot of this system initially. There's some water present inside it. When I take a snapshot, this defines my initial state. And then after a while, I take a snapshot of it again and I see something has changed and that defines my final state. So going from initial state to final state, how much water quantity has changed? How do we calculate that? We simply say final minus initial. My final value was 40, my initial value was 20, my change is 20. Final minus initial. So you have to talk about final minus initial. There's sometimes students feel that because they did not get good grades in class 10th or because they did not clear a certain exam or there are other peers who seem to be scoring better than them. And that may seem discouraging, but it's not discouraging if you think about change. A student can start ahead of you, and if he does not focus on change, and somebody who's not starting at such a better level, but focuses on change, focuses on improvement, can reach a much better place. So focus on change. Don't focus on where you are, focus on where you want to go. All right. Another thing that we're going to mention here is internal energy is a state variable or function. Let me just clear the board. So internal energy is a state variable or function. And what is a state variable or function? It's a function that is defined by the current state of the system. It does not matter where you come from. It does not matter where you're going to go next. I can look at the system and tell about its internal energy. In terms of state variables, if I draw a graph, right? In thermodynamics, whenever we draw a graph, what do we mean for there to be? We mean for there to be state variables. In coordinate geometry, you use distance as a measure. Distance doesn't make a lot of sense in thermodynamics. What makes sense is state variables such as pressure, such as volume. In general, we'll be taking a 2D graph, although you can have a 3D graph. You can draw temperature, you can draw number of molecules over there. But for simplicity, so that I can draw on this board, we're going to take two-dimensional graphs. So what do we mean when we say internal energy is a state function? Internal energy is a state function because once you define your state, once you fix on a pressure, once you fix on a volume, you have defined your state. It doesn't matter where you came from, it doesn't matter where you're going to go. Your state is defined at this particular point and it is fixed. So this is what we mean by state variable. I could like to illustrate that it doesn't matter where you come from, you could have come from a different path and you could be going on a different path. But at this point, the state is defined. So the history doesn't matter, future doesn't matter. Some way you can think about it like that. State is defined by the state variables. And you can look at the diagram for doing this. Another point that I'd like to mention over here is the point about delta U. Delta U is U final minus U initial. So if I draw another graph, once again, on the axis, what do we have? We have state variables. Some state variables, usually you'll find PV written. So if I go from point A is a state, right? It's in the space of state variables. So it's a state. And we're going to go to point B, another state. So at this point, is internal energy defined? And the answer is yes, it's a state variable. Once you fix, it's a state variable function. Once you fix others, pressure, volume, your state function is also fixed. Internal energy is fixed. So you can write internal energy at point A. At point B, once I fix state variables, I have UB also fixed. Now, delta U. Suppose I go from A to B. Suppose I go from A to B. Then delta U, does it matter how I go from A to B? If I go from above, if I go from something like this, if I take a more interesting path. So I have path 1, I have path 2, I have path 3. So if I go from either of these paths or any of these paths, delta U is not going to change. Why? Because initial state and final states are already defined. Because initial states, delta U is written as UB minus UA. If final and initial states are defined, then it doesn't matter. It doesn't matter which path you take from A to B. As long as you reach B, your internal energy change stays constant. So it does not depend on the path. Delta U does not depend on the path. Now, time for first law of thermodynamics. First law of thermodynamics tells us a lot of things. Some very intuitive things, some very non-intuitive things. It's surprisingly simple, but very, very dangerous. Surprisingly simple, but very dangerous. Let's see. This is the statement of first law of thermodynamics. Something very simple. The change in internal energy of an isolated system is 0. It's very intuitive as well. If you have an isolated system, it's not going to change. It's not going to change. If you think about it, if you isolate yourself, you're not going to change much. If you don't interact with people, if you don't read things, if you don't interact with the world around you, you're not going to change. You're going to stay the same. Your growth is going to stop there. So interaction is important. Interaction is very important. For an isolated system, internal energy does not change. If that is the first law of thermodynamics, it's not a lot of fun, is it? I just have to take an isolated system and I say, voila, the energy of this system is not going to change. Thank you. Like I should get a prize for saying that. But we also have to talk about delta U, not isolated systems. How do we define these things? right? If a system can interact with the world, if a system can exchange heat, if a system can do work, if a system can exchange mass, then how is the internal energy going to change? That also comes under first law of thermodynamics. First law of thermodynamics not only tells us that the energy of an isolated system does not change, it also tells us how the energy of a non-isolated system changes. There is one point, one very subtle point that we need to cover. One very subtle point that we need to cover, and we're going to do that using graph. Suppose I have an isolated system. Once again, I draw my state variables P and V. I have an isolated system. An isolated system has some defined points over here, and this is the energy of my isolated system defined at this point. Now, what can this point do? Can this point go up? It can't go up because delta U is non-zero. It's supposed to be zero. Isolated system is not supposed to change its internal energy, so it can't move. So initial, final state can't be different for an isolated system. But what if I do this? What if I do this? What if I go and come back to the same point so that my initial and final points are the same? If my initial and final points are the same. In this case also, my delta U is zero. My delta U is zero because if I label this point as A, my delta U is simply UA, which is my final state, minus UA, which is my initial state, and I get 0. Does this mean my system is isolated? The answer is no, because my system did something in the middle. It did something in the middle, right? It's not an isolated system. If it was an isolated system, this wouldn't exist. This whole drama wouldn't exist. So what is the correct statement of first law of thermodynamics? It's not that delta U of isolated system is 0. It is that du of isolated system is 0. Right? Maths आ रहा है बच्चों. du, delta U, पता नहीं क्या बोल रहे हैं. Don't get scared. It's very easy, very simple things. Du means small changes. So delta U means big changes, that even when big changes can be 0, the system is not isolated. We have to talk about small changes. And when I say du of isolated system is 0, that means I can't change it even a little. I can't go from A point to here. I can't try to move it even a little bit. All these things are not allowed. So even small changes in an isolated system's energy are not allowed. But we also have to talk about the change in energy of a not isolated system. And we'll see about that. The question is, how can we change the energy of a non-isolated system? How can we change the energy of a non-isolated system? Now what I want you to do is I want you to imagine a block. And what can you do to this block to change its energy? What can you do to this block to change its energy? It's kind of a thought experiment. Think about it. I want to change the energy of a block. I'll draw a block here. This is my block. Suppose it's kept on the ground. What can I do to change its energy? One guy will say, pick it up, leave it somewhere else. So there's another place and I pick it up and I leave it over here. Have I changed the energy of the system? I haven't. I have not changed the energy of the system. In the process, the energy of the system was different because the block has moved. So there was some velocity. But overall, in this case, delta U is not 0. Delta U is 0. Alright, so what can be done to change the energy of the system? Some of you are thinking we should lift the block. And you are correct. Because internal energy also includes potential energy of the system. So if you lift the block, potential increases. So now we have changed the energy of the system, and some of you are thinking, I will kick the box. लात मारो इसको, खींच के. And if you लात मारेंगे, velocity आएगा. Velocity आएगा, kinetic energy आएगा. So once you have kinetic energy, you have also changed the energy of the system. So you can lift it, you can change its potential, you can change its kinetic energy. All this. What are you doing? What are you doing? Some of you who like to read physics, what is it that you're fundamentally doing in all of these things? And the answer is you're doing work. You're doing work by lifting the block against gravitation. You're doing work by pushing the block, giving it a velocity. So moving the block, lifting the block, moving the block, lifting the block, you do some work. Now, how else can I change the energy of this block? How else can I change the energy of this block? If you have been paying attention, in thermodynamics, we have been talking so much about heat, about temperature, it's in the name, thermodynamics, thermal effects. So the next step that we can do is we can heat the block. We can heat the block to change its energy. When we heat it, the energy increases. And that is correct. So notice the two symbols that there are. There is work. There is Q, which means heat. Q, which means heat. Remember this, H is not heat. Q is heat. So we can change the energy of a non-isolated system using work and using heat. Using work and using heat. Now we want to talk more about work, more about heat. We want to understand them properly before moving on. So I'll just quickly, we are going to mention the internal energy of an ideal gas. Internal energy of an ideal gas, which is monoatomic. What does monoatomic mean? It means a gas made up of single atomic particles. Example would be helium, example would be neon. Most ideal gases are monoatomic. Actually, all ideal gases are monoatomic. There is argon, there is xenon. All these ideal gases are monoatomic. And the energy is given by 3/2 nRT. We will talk about why, but keep this formula in mind. When we talk about why, you will understand it. 3/2 nRT is the internal energy of a monoatomic gas. Only monoatomic. If I have a different type of gas, nitrogen is not monoatomic. Nitrogen has N and N, two atoms. It's a diatomic gas. The internal energy is not 3/2 nRT. It's not 3/2 nRT. And now I have a question for you. What is the molar energy of a monoatomic gas? What is the molar energy of a monoatomic gas? First you have to ask, what is molar? Molar means per mole. It means when you take only 1 mole of the gas. So it's very easy. You say molar energy, you already know the formula for energy. Formula for energy has N in it. If we replace N with 1, we get molar energy. So your answer of U molar should be 3/2 RT. 3/2 RT. So this is your molar energy of an ideal gas. So 1 mole of a monoatomic ideal gas has the energy 3/2 RT. 3/2 RT. Some very interesting things about this. Your physics teacher might tell you in the class for kinetic theory. And things are very simple. The first observation over here is 3/2 nRT can be written as 3 times 1/2 RT. 3 times 1/2 RT. There's a factor of 3, there's a factor of 1/2 RT. And this corresponds to the energy of an ideal gas. How can ideal gas have energy? A particle can go forward, it can go left or right, it can go up or down. 3 ways. 3 ways it can go, and each way has 1/2 RT. So in total, 3/2 RT. That's the molar energy of ideal gas. Alright, keep this formula in mind. Just note it down. We will understand it later, but this will help you solve some questions. It will also help you understand some concepts about heat, work that we are going to discuss. Let's talk about heat. What is heat? How do we take some time, note all this down. I have written a few things. Take some time. All right, moving on. What is heat? It's related to random motion. Just like we talked about temperature relating to random motion. Heat is also related to random motion, randomized motion of molecules. Molecules just bouncing about crazy, bouncing about crazy. That's what heat is. More heat, more craziness. More heat, more craziness. So you can, if you think about kids have a lot of heat, just running around mindlessly. I mean, you look at kids, what are they even doing यार? पता नहीं क्या कर, कोई उधर भाग रहा है, कोई उधर भाग, कोई दीवार में जाके भिड़ जाता है. So much heat, so much heat. But as we grow up, our heat reduces. We walk around slowly. We are more poised, I'd say. So heat related to random motion. More heat, more craziness. And question that we should ask, higher temperature, does it mean more heat content? Very interesting question. Very interesting question. Think about it. Think about it. Does having higher temperature mean more heat content? Higher temperature. Suppose I take one object at 20 degrees Celsius, another object at 40 degrees Celsius, which has higher heat content, more heat content. The answer is very, it's very surprising. Higher temperature does not mean more heat content. How can I put this? Think of it like this. I have a very small object at 40 degrees Celsius. Now I have a very large object at 20 degrees Celsius, right? This is 10 grams, this is 1 kg. 10 grams, 1 kg. Now, which has more heat? If I drop this into water, the temperature of water will not change by much. But this temperature will change very easily. If I drop this into water, it will change the temperature of water itself. Because here you have higher mass present at a lower temperature. So it might have more heat content. You can think of it like you take a block of ice. Will this small object be able to melt the ice? Maybe not. Will this large object be able to melt the ice? Maybe. But before that, we also have to define what heat content is. And to be honest, the question is moot. There is nothing like heat content. You should not say things like heat of something. How much heat does something have? How much heat does something have? So higher temperature does not mean more heat content. More specifically, there is nothing like heat content. We should never say how much heat something has. We should never say that. Never say that. Heat content of a state cannot be defined. This is not the right thing to say. Heat is a path function. We cannot define heat content of a state because heat is a path function. It's not where you are, it's not where you reach, it's how you go from where you are to where you reach that matters. It's how you go from where you are to where you reach that matters. Let me do a diagram to help you. So I have pressure over here, I have volume over here. Once again, pressure, volume, state variables. You can imagine another axis, temperature, number of particles present over here. I go from point A to point B. I go like this, I go like this, I go like this. So I have 3 paths, 1, 2, 3. Earlier we mentioned that going from A to B, internal energy change is the same because initial state is defined, final state is defined, internal energy change is same. Delta U is same for 1, 2, 3. But heat is not the same. If we take Q, Q is not the same. Q for 1 is not equal to Q for 2, is not equal to Q for 3. Q for 1 not equal to Q for 2, not equal to Q for 3. So we have to be careful which path we are taking. Next, work. You might remember force definition, earlier classes. Let me just write it down. Work is equals to force dot displacement. This is the definition you might remember. Force dot displacement. Force multiplied with displacement. This force is a vector quantity. Displacement is also a vector quantity. Dot product is a scalar quantity. Dot product is also known as scalar product. As a result, my work is a scalar quantity. More specifically, it's the integral of force dot ds. It's the integral of force dot ds. You take small changes. Small displacement, how much force? Force times displacement, add it. Small displacement, how much force? Take a dot product, add it. You keep doing that. That is what integral means. So your work can be defined as integral f dot ds. Right? The things that matter over here is that we have to take force and displacement. And if you have force acting like this, if your displacement is in this direction, what do? We take the dot product. Dot product means take a shadow. And whatever the shadow is, the perpendicular direction is your work component. Right. But in thermodynamics, we don't usually come across cases like this. In thermodynamics, we usually come across pressure. We never talked about force when it came to state variables. But we talked about pressure, we talked about volume, we talked about temperature, we talked about number of particles. So we have to define things in those terms. We have to define things using pressure. All right. So let's clear the board and see what we can do. We're going to define a piston over here. A piston which looks something like this. Piston has a movable component. And what is my movable component? My movable component is the head of the piston, which can go left or right. I have some gas particles present. Some gas particles are present inside the piston. And these gas particles, and when you move it, volume increases. When you move it left, volume decreases. So now we have to find a similar definition to work that we had earlier. Work is equals to force times displacement. So here we don't have force. Here we have pressure. We have pressure internal. I'm going to write P internal, which is the pressure due to gas present inside the piston. And I also have P external. Right? Outside also there is some gas present. There's some gas present outside also. Now, if this piston is not moving, which is higher, internal, external pressure, or are they same? If this piston is not moving, then internal pressure is equal to external pressure. That is called the state of equilibrium. But then suppose P internal is not same as P external. If P internal is less than P external, then the P external starts pushing. If P internal is more than P external, then internal side starts pushing. Right? Internal side starts pushing. Alright. So the way we define work in thermodynamics is we're going to write similarly force times displacement. Suppose this piston moved from this point over here to this point over here. So we have 2 points present from x to x plus dx. This distance between them I'm going to write dx. What does dx mean? Dx means small displacement. That's it. Dx means a small displacement. I moved the piston from here to here in a small displacement. What am I going against? I'm going against P external. Right? So how much force is P external putting on me in the piston? How much force is P external putting on me? And that depends on the area of the piston, right? So whatever area of the piston is, if I multiply that with P external, I get force. So force is equals to P external times area. P external times area. I'm just going to write modulus of force. Modulus of force is P external times area. And now, when you move dx distance, your work done is the dot product. Now just see, dx is in this direction. dx is in right direction, external pressure is in left direction. They're opposite to each other. Opposite to each other, dot product has a negative sign. I can write dw is equals to minus PA times dx. This is my force, this is my displacement. So dw is equals to PA dx. We're going to rearrange this term over here, A dx. If you multiply the area of the piston by this, you get the volume covered. In terms of 3D, if you think in 3D aspect, what do you get? Your piston has moved from here to here. You have dx, you have area A, and you can check. That this area times dx gives you this small volume, which is dv. So dw is written as minus p external dv. And how do you calculate the total work from small amount of work? You integrate it. The total work is the integral of, there's a negative sign, p external dv. Did you understand? समझ आया क्या? Work done, negative integral p external dv. Yeah, a very simple calculation. You'll see it in physics as well. If the visualization is not very clear, I suggest watch some videos. Take a look at how exactly this piston moves up and down. How does area times dx gives the volume inside it. Watch some videos. Definitely watch some videos. But this formula, keep it in mind. Work done is equals to minus integral of p external dv from initial state to final state. So whatever initial state is and whatever final state is, and when you integrate it, you get work done. If you understand this much, it's enough to solve questions. If you can memorize this, that is also enough to solve questions. But I highly recommend you go through this derivation at least once, rewind the video, try to solve it one more time. I highly recommend you go through this. Derivation one more time. So, if you understand this formula, we should talk about work of a state. Similar to heat content, work of a state cannot be defined. Work of a state cannot be defined. You can't say what work this state has. That would be like saying integrate from this state to this state. How do I integrate from initial to final when I don't have an initial and final? State doesn't have an initial and final. It has a fixed point, right? We need an initial point. We need a final point. Work is a path function. We need an initial point. We need a final point. Work is a path function. Never talk about work of a state. Talk about work of a process. And there's one more very easy interpretation of the same thing. Let me clear the board and talk about this. We're going to talk about the area diagram. So intuitively, how do we understand work? See, all that derivation is fine. All that is. Some of you who like maths can do this. Some of you don't have maths, so integration is difficult. So you don't have to worry about that. We have a very intuitive way of understanding this. The work done equals minus integral of px dv. This means that if I draw the graph of P external and volume, and if I have a process going from one point to another, if my initial point is A, my final point is B, I'm going from A to B, then my work done is given by this area, and this area should be multiplied with a negative sign. So I'm going to write minus A. Why negative sign? Why should I write minus A? Because our system is expanding. Think of it like this. If the piston moves outwards, if the piston moves against atmosphere, then it has to do some work. And if it does some work, its own energy reduces. आप अभी बैठ जाइए, study for 1 hour, you will feel a little tired. You need a break. Then you study for another hour, you'll feel a little bit more tired. When you work When you work, your energy reduces. That makes sense, right? You do something, your energy reduces. But sometimes you do nothing and still you get tired. That happens with humans, not with these guys. If some of you have trouble like falling asleep, if you don't feel tired or sleepy in the night, and you stay up late nights, try exercising, try doing some extra work so that your energy reduces and you get a good night's sleep. Similarly, when you expand, your volume is increasing. When you expand, your volume is increasing, your work should be negative, because negative work means it reduces the energy of the system. Reduces the energy of the system. Similarly, if you contract, if I take the same process, instead of going from A to B, I go from B to A. This time, the system is being pushed upon. The surroundings is pushing on the system. That's something like your parents coming to scold you. Like you're lazing around, you don't have any energy to study. Like you're just like, I'll just watch something and I'll just like, I'll do nothing. I'm too lazy today. And then your parents come like, what are you doing here? Your exams are coming up. You should study. Other people so like uncle's son is studying 12 hours a day. This uncle's son is studying 13 hours a day. He wants to crack IIT-JEE. He wants to do this. You just want to lie around. And that scolding is pushing onto you. Surroundings are pushing onto you. Right? Surroundings are pushing on you. That increases your energy. That should increase your energy because they mean the best for you. So you get up and you work a little. Sometimes we need more pushing from surroundings to increase our energy. So when you're contracting, when your volume is reducing, your energy increases. So in this case, we take plus A. Right? One way to imagine this is expansion means negative work and contraction means positive work. Expansion means negative work, contraction means positive work. So when surroundings push onto you, your energy increases. When you try to push onto surroundings, your energy decreases. There's no point in fighting back with your parents here. There's no point. Right? They're much older than you. They're like, तुम्हें तो देखा है हमने, like तुम्हारे तो कपड़े भी चेंज किए, तुम्हें तो चलना भी सिखाया, तुम्हें बोलना भी सिखाया, तुम हमें क्या बोलोगे? Right? Same thing. There's no point in pushing onto like the surroundings. Your energy decreases. When surroundings push onto you, your energy increases. Take that as motivation. Don't take it as something is bothering you. Don't take it as something is scolding you. Your parents mean the best for you, and you should try and make the most of it. Right? Like not everyone's parents are going to push like do whatever you want yaar, kuch bhi kar le, kya fark padta hai hame to. Like don't, like if your parents are scolding you, that's a good thing. They care for you. They want you to work harder. So when surroundings push onto you, your energy increases. Sign convention. Like just we talked about work. Work positive kab hota hai? Positive when somebody pushes onto you. When there is deflation. Work negative kab hota hai? When we push onto the surroundings. When we use energy to expand. Similarly, delta U, which is Q plus W. This is the first time I'm saying this. Very carefully. Look at it very carefully. We said that you can change the energy of the block using heat. You can change the energy of the block using work. So total energy change is the sum of both of them. Thoda sa heat se aayega, thoda sa work se aayega. You add them up, you get total change in energy. Right? Total change in energy is the sum of change in energy due to heat. It's the sum of change in energy due to work. And we have to talk about sign conventions. We just talked about work's sign convention. If the surroundings are pushing onto you, if there is deflation, work done is positive. That increases the energy of the system. Right? Delta U increases if work is positive. Similarly, if you heat the system, should the energy of the system increase? Should the energy of the system decrease? If you heat the system, should the energy of the system increase or should the energy of the system decrease? The answer is obvious. If you heat the system, it should be positive. So positive when you increase the system's energy. W is positive, increase the system of energy. Q is positive, increase the system of energy. SI unit of energy is joules. SI unit of energy is joules. What does that mean? That means that the unit of heat, unit of work is also joules, right? Joules equals joules plus joules. That makes sense, right? You can't be like joules equals joule plus Newton. You can't do that. So because SI unit of energy is joules, SI unit of heat is also joules, SI unit of work is also joules. Alright, now we're going to start talking about some specific examples. We're going to see how to apply first law of thermodynamics to certain special cases. And the first case we have is adiabatic walls. In adiabatic walls, what happens? What is heat transferred? याद आया कुछ? याद करो. What is adiabatic system boundary? And what is it related? How is it related to heat? In system boundary, if you remember, heat cannot be exchanged in adiabatic walls. Heat cannot be exchanged in adiabatic walls. So the answer to the first question is that Q is equals to 0. Q equals 0. Adiabatic walls. The next thing we have is change in energy. Very interesting question. So using the first law of thermodynamics, try to find out what is delta U. What is delta U? We already know what is Q. Q is 0. Using the first law of thermodynamics, try to find what is delta U. The answer is that delta U, which is equals to Q plus W, because the first law of thermodynamics, if Q is 0, then delta U is simply equal to work. So in case of adiabatic walls, the change in energy happens only with work, not due to heat. Moving on, rigid walls. What is the work done? Once again, try to remember, दिमाग लगाओ. Rigid walls के अंदर work कैसे? How do we find work in rigid walls? If you have remembered it, very nice. But if you can't remember it, we just defined work. What is the definition of work? It's the negative integral of pressure dV. Right? Negative integral of pressure dV. Rigid walls. What do rigid walls means, and how can I use it in the definition of work to find work? And the answer is work done is 0. Why is work done 0? If dV is 0. If there is no change in volume, then you can't have any integral. This integral is also 0, because something multiplied with 0 is 0. So for rigid walls, work done is 0. If you don't move, you can't do work. Any rigid system can't do work. It has to be active. It has to be moving. Right? If you just sit around idly, you can't do work. So थोड़ी मेहनत करनी पड़ेगी, but काम चल जाएगा. थोड़ी मेहनत करनी पड़ेगी, but काम हो जाएगा. Now the question is, what is delta U? Using the first law of thermodynamics, what is delta U? And the answer, very simple. We first write the thermodynamics, delta U, first law of thermodynamics is equals to Q plus W. And we said rigid walls, work done is 0. So delta U is equals to Q. So when you have rigid walls, you get delta U equals Q. Very important. It's going to help us in defining so many things. It's going to help us in defining heat capacity of the system. Very important. It's going to help us in defining heat capacity of ideal gases. A lot of questions are asked from heat capacity of ideal gases. So delta U equals Q, but what is the condition? dV is 0. Change in volume is 0. You can't increase or decrease the volume because your walls are rigid. Alright, moving on to applications. This is probably the most fun part for you. You have to use your brain. You have to try and solve this question. Alright, choose the correct statement for adiabatic rigid walls. Abhi discuss kiya tha, last 2 slides, adiabatic rigid walls. In case of adiabatic walls, what is special? What do we have to remember in case of adiabatic walls? In case of adiabatic walls, Q is 0, heat exchange is 0. In case of rigid walls, work done is 0. So which of these statements is correct? Delta U equals Q, no, Q is 0. Delta U equals W, W is 0. Delta U equals Q plus 2, this is true. This is true in general. This is true in general, but given the conditions, the answer should be delta U equals 0. Because Q is 0, W is 0. So we don't have to write the general case because we know that it's not a general case. It's a very simple case of Q equals 0, W equals 0. In terms of types of system, what does it mean? In terms of types of system, it means isolated system. So our answer is none of these. Delta U is simply 0. Let's take a note of this. Both the conditions, adiabatic and rigid. Alright, next application. What do we have? A piston's volume increases against atmosphere. What is the correct statement? Take a moment, think about it. We just discussed about it. We just discussed about the sign convention of work. Sign convention of work. Work greater than 0, work less than 0. When is work greater than 0? When is work less than 0? When is it equal to 0? We just talked about it. So, a piston's volume increases against atmosphere. What is the correct statement? Alright. So, one thing that I can tell you while solving these questions is try to draw diagrams. Try to draw as many diagrams as you can. Because diagrams are going to help you visualize this. So it says that piston's volume increases against atmosphere. So let's draw a piston. There is piston and there is atmosphere present. So I can write 1 atm pressure from outside. There is some gas present inside, right? No problem. Now it says volume increases. If I try to show it over here, that means piston is moving towards right. And if I draw the graph, pressure 1 atm, its volume is increasing. So there is V final which is greater than V initial. That means I'm going from left to right. This is my initial state. This is my final state. So in this case, how do we find the work? First thing you should always remember, work is the area under the graph. Area under the PV graph. If I have pressure over here, if I have volume over here, if I have pressure over here, if I have volume over here, then the work is given by area under the graph. And now, whether it is positive or negative, if a system is pushing the atmosphere, then it is using its own energy to do it. Like piston is using its energy to push against the atmosphere. As a result, work done should be negative. Correct answer is, sorry, this does not make sense. Since volume is increasing against atmosphere, work done should be less than 0. Because if the piston pushes outside, it uses its energy. So its internal energy decreases. If its internal energy decreases, then work is less than 0. Alright, next. An ideal gas expanding into vacuum, cools down, heats up, same temperature, depends. Right? Think about it. You've probably seen it somewhere. In many movies, when a gas expands in vacuum, they show some freezing kind of effect. But here we are talking about ideal gases. This is also known as Joule-Thomson effect. In case of ideal gases, the expansion into vacuum, same temperature. Nothing happens if an ideal gas expands into vacuum. One way to think about this is that if you're expanding into vacuum, external pressure is 0, so you don't have to do work against anything, you don't have to waste any of your energy, you stay in the same temperature. So the correct answer is option C. Now a real gas expands. If a real gas, what's the difference between real gas and ideal gas? Ideal gases follow the equation of state PV equals nRT. Real gases, in case of real gases, this is not true. PV is not equal to nRT for real gases. So when a real gas expands into vacuum, does it cool down, heats up, same temperature, depends on something. And the answer is The answer is it depends on something. It depends on something. Mostly it will cool down. You need to have very specific condition for a gas to heat up as it expands into vacuum. Mostly gases will cool down as they expand into vacuum, but to be very accurate, it depends. Next question, a system with rigid walls absorbs 20 joule of heat, delta U equals question mark. What is the change in energy if the system with the rigid walls absorbs 20 joule heat? Alright, so first thing that we're going to talk about, rigid walls, work done is 0. Work done is 0. Why is work done 0? Because change in volume is 0. If change in volume is 0, work done is 0. Delta U is written as Q. Delta U is written as Q. Just to be a little more specific, we write volume is constant and delta U equals to Q. Q is already given to us, absorbs 20 joule heat, and the answer is delta U equals 20. It's absorbing, so its heat, the absorbing increases the energy. As a result, delta equals plus 20 joules. The correct answer is option A. It is equal to 20 joules. Next question. Now we are in the self-stimulator part of the question. Here we're going to see what mistakes you can make. We're going to try and catch those mistakes and correct them. This time, a system with movable walls absorbs 20 joule of heat. So what happens? What is the change in energy? Take a moment, think about it. Do a thought experiment. Very important. Thought experiments are very important. And let's go ahead. Very simple. Delta U should be 20 joules because it's not given to us what work is done, what work is not done. So the answer should be delta U equals 20 joules. There is no information about work done. We can assume work done to be 0. Is that correct? No, it's not correct. You can't assume things like that. So we have to make an educated guess about work done. Work done is not 0. So let's do a thought experiment. We have a system with movable walls. Very simple system with movable walls is a piston. If I add heat to it, what is going to happen when you heat the system? Usually when you heat the system, it expands, right? Usually when you heat the system, it expands. Very simple example. You take water, you heat it, you make it into steam. Steam expands, right? Unlike water, steam expands. Other examples, you take a block of metal, you heat it, it expands. You take almost all substances that you can think of, when you heat them, they expand. And what does expansion mean? Does expansion mean positive work or does expansion mean negative work? Does expansion mean positive work or does expansion mean negative work? And the answer is expansion means negative work. So our educated guess is work done is less than 0. Work done is a negative quantity because on heating the work done is expansion occurs, and as a result work done is negative. Now if I write the first law of thermodynamics, I write delta U equals Q plus W. Q is given to us 20 joules. We know that work done is less than 0, so there is plus negative quantity present, some negative quantity present. So the answer is less than 20 joules. In certain cases, work done might be very low negative, like if the expansion is very little, because we are only adding a very small amount of heat anyway, 20 joules. So maybe the expansion is very little, maybe the object is so large that adding 20 joules of heat does not make it to expand a lot. So it's possible that it's either negative or maybe very close to 0, and it can be either A or C. So I would say that the best guess that we can make is delta U is less than or equal to 20 joules. So maximum to maximum it is 20 joules, but it is less than or equal to 20 joules. And the answer is option D, which is A or C. Right? When information is not given to you, don't assume. Don't assume. Don't assume work to be 0 simply because it's not given to you. Try and make a educated guess. Alright, let's move on to the next self-simulator. Gas expanding into vacuum does positive work. Gas expanding into vacuum does positive work. Think about it. Pause the video. Alright. So what do we see? We see something is expanding. Expanding, how do I draw the diagram? We say pressure and volume. And we say that going from A to B like this, it is expanding, and my answer should be minus A. If I'm going in this direction, minus of this area. So I should get negative value. Gas expanding to vacuum does positive work. Right, the answer should be B. But the answer, the real answer, so the answer is correct, but the reasoning is wrong. The answer is correct, but the reasoning is wrong. The reasoning is wrong because it's not minus A. It's not a negative area. It is simply 0. It is simply 0. It's not minus A, it is 0. Why is it 0? Because you are expanding, but you're expanding in vacuum. You're expanding in vacuum. And as a result, you expanding in vacuum, you're not doing work against anything. You're not working against anything. If you're not working against anything, you can't do work. You can't do work by going against nobody. Right? You always have to have a little bit of difference to do some work. If everyone is along with you, you're not doing any work. Right? You're not doing any work if you're not going against something. So going against vacuum, work done is 0. Going against vacuum, work done is 0. It's not positive. It's not positive. The answer is B. The answer is B. Alright guys, I hope you guys understood a few things that came today. We did some intuitive explanation of work done. When is work done positive? When is work done negative? When there is expansion, work done is negative. When there is contraction, deflation, work done is positive. We talked about other things, talked about internal energy, we talked about heat. We defined the internal energy of an ideal gas. That's a formula that you should remember. And now let's see what's next. And next we have lecture 4 of thermodynamics. We're going to talk about types of processes. Types of processes. We're going to talk about heat capacity. And the formula for ideal gases is going to help us over here. We're going to talk about equipartition of energy. Using equipartition of energy, we will be able to explain why the energy of an ideal gas is 3 by 2 RT. Why the energy of ideal gas is 3 by 2 RT. Alright guys, until next time, have fun, practice a lot of questions, take care, stay safe, stay healthy, and keep working hard. Keep working hard. This is Rakesh Aarya signing off, and well, have a nice day.